All right, here's an example from mechatronics looking at actuator loads on actuators. This problem, oops, I copied two of them by accident. We're just looking at this guy. Determine the size of shaft needed to run a 500-watt generator. Assume the shaft is made out of steel. Okay, so let's start with a schematic. In our schematic, we'll have, I don't know, there's something, some turbine. We'll call it a turbine in this case. It has a shaft. Shaft connects it to a generator. And of course, then the generator has leads coming off. We create some voltage. We have a load. So in this case, we're interested in the shaft. So we need a free body diagram for the shaft. So our free body diagram will look like all I'm doing is transmitting a torque. So I guess I'm gonna have a torque at one end. Notice I'm drawing it two ways. You know, technically, we like to draw it with this double arrow to indicate it separately from a force because it is a vector going in a direction, but I'm giving it the little curly guy just to kind of remind us that it's a torque. So I'm looking for this torque. So the torque, I need the torque. Well, I'm given that it's a 500-watt generator. 500 watts is power, so I can go jump and look at my sheet that relates power. I'm jumping to the sheet that says force, torque, work, energy, power, and it tells me that power is given as T dotted with omega, or in this case, I'll assume they're in the same direction. So I've got my power, which is 500 watts, equals pause. So let's see, we get 500 watts equals torque, and I'm going to assume that T is parallel to omega, so that means I can multiply that times omega. Generator is running at 60 hertz, so that means I get 60 cycles per second times 2 pi radians per cycle, or T is 5,000 divided by 60 times 2 pi. Okay, so that's my second step. My third step now is to calculate my stress. My stress in this case is going to be shear stress. So it's going to be our torsional shear stress. And that will be tau equals TR over J. So I can start plugging these in. I get 5, okay. All right, so I'm gonna plug those in. Now what I'm looking for, which is TR over pi, let's see, what do we say, pi halves times R to the 4th. Okay, and that has to be from my max shear stress theory. If I compare it to my max shear stress theory, I can see that tau max is equal to the yield stress divided by 2. And here I have a factor of safety of 1.5. That's my factor of safety. So that means that putting all this together, T times R over pi halves R 4th has to be less than or equal to, we'll take the equal to, SY over 2 times 1.5. We'll solve for R, that's R cubed, so T over pi halves times 2 times 1.5 divided by S yield is R cubed. And we can now solve for R cubed. Okay, so we put in 5,000 times 2 times 1.5 divided by 60 times 2 pi times pi, oops. Yeah. Divided by 2 times my yield. What's my yield? 450 megapaw. R cubed. Okay, so we'll go down here to MATLAB and solve for R. So I get 5,000 times 2 times 1.5 divided by that by the quantity, 60 times 2 times pi divided by 2 times 415 times e to the 6th. I get that guy. We're going to take the cube root of that, so ANS to the 1/3. And we get a shaft size of 0.0039 meters, or 3.9. R is 3.9 millimeters. Okay, pretty small shaft. But, you know, the bare minimum, I guess that's what we need. Hey, keep in mind, that is the note here. Okay, I want to show you guys something. So this P equals T times a mega, right? So for a 5,000 watt generator, as long as I'm running at this speed, my torque is here. Imagine the speed goes larger. If this is the speed down here, this is a mega. If the mega increases, the torque decreases. If the mega decreases, the torque increases. So if I'm trying to pass 5,000 watts of power and I have a slower speed, my torque demands are going to be higher. Keep that in mind. Okay.